The ground under Ayacucho did not just shake, it rolled. For nearly a full minute, an entire stretch of the Peruvian Andes swayed like the deck of a ship, and 11 million people more than 400 kilometers away, in Lima, felt the floor move beneath their feet. Rocks tumbled down hillsides near a small town called Coracora. Families ran into the streets, holding each other, waiting to see if their homes would still be standing when the shaking stopped. And somewhere beneath their feet, roughly 100 kilometers down, in a place no human being will ever see or touch, 2 tectonic plates had just released decades of stored energy in a matter of seconds. This was not a random event. It was not bad luck. It was the latest chapter in one of the most closely watched geological stories on the planet, and scientists have been waiting, quite literally, for something like this. On Thursday, August 20th, 2026, at 1 p.m. local time, a powerful earthquake struck the Ayacucho region of southern Peru. Peru's Geophysical Institute, known by its Spanish acronym IGP, measured the quake at magnitude 7.2. The United States Geological's L survey, using a different global monitoring network and slightly different data processing methods, initially placed it at magnitude 6.7. Both numbers describe the same event, and the gap between them is not a mistake or controversy. It is simply what happens in the first hours after a major earthquake, when different seismic agencies around the world are racing to process incoming data from their own networks of instruments before their estimates converge. The IGP located the epicenter about 35 kilometers north of Coracora, a town of roughly 10,000 people in the Parinacochas province of Ayacucho, at coordinates of 1470 degrees south latitude and 73.78 degrees west longitude. The USGS placed its epicenter slightly differently, closer to a location called Upahuacho, but in essentially the same general area of the southern Peruvian highlands. What makes this earthquake worth understanding is not just its size, but its depth. The IGP measured the focus of the rupture at 108 kilometers below the surface. The USGS put it closer to 67 kilometers. Either way, this was what seismologists call an intermediate depth earthquake, originating far beneath the crust, inside the slab F oceanic rock that is being forced underneath the South American continent. That depth matters enormously because it explains almost everything about how this earthquake behaved on the surface. Despite carrying the energy of a magnitude 7 event, the shaking felt in Coracora, the town closest to TEH epicenter, registered only an intensity of third to IV on the modified Mercalli scale, a measure of how strongly people and structures actually experience the shaking, as opposed to how much energy the earthquake released at its source. Intensity 3 to IV is moderate. People feel it clearly. Oh, BX, rattle. But it is far from the violent, structure-collapsing intensity you would expect from a shallow magnitude 7 quake breaking just beneath a city. The depth acted like a cushion, spreading and dampening the seismic waves before they reached the surface directly above the rupture. But that same depth is also why the earthquake was felt so far away. Deep earthquakes radiate energy differently than shallow ones. Instead of the shaking being concentrated in a small radius around the epicenter, the seismic waves travel more efficiently through the deeper, denser rock of the Earth's upper mantle and lower crust, allowing them to reach the surface across an enormous geographic footprint before losing their strength. That is precisely what happened here. Residents in Ayacucho felt it strongly. So did people in Ica, Huancavelica, and Arequipa. Tremors reached as far as Cusco and Tacna to the southeast, and reports of swaying buildings even came from La Paz, the capital of neighboring Bolivia, more than 500 kilometers from the epicenter. And in Lima, Peru's capital and home to more than 11 million people, residents on upper floors of apartment buildings felt the unmistakable, slow sway of a distant but powerful earthquake passing beneath the entire western edge of South America. In the immediate aftermath, Peru's civil defense agency, known as INDECI, along with the mayor of Coracora, began surveying the damage. Initial reports described landslides on the slopes surrounding Coracora, rockfalls tumbling down hillsides, and cracks appearing in some structures. Later assessments confirmed damage to homes, schools, and health centers scattered across the Ayacucho region, the kind of structural harm that accumulates in rural Andean towns built from adobe brick and unreinforced masonry, materials that were never engineered to withstand strong shaking. Yet remarkably, in the hours and days that followed, authorities reported no deaths and no serious injuries. Hernando Tavera, the executive president of the Geophysical Institute of Peru, told local media that based on the intensity levels recorded at the surface, significant damage was not expected, and that assessment largely held. The mayor of Coracora described a population that responded quickly and calmly, evacuating homes and gathering in open areas, a reflex built from generations of living in one of the most seismically active countries on Earth. Peru's tsunami warning system also confirmed there was no tsunami threat from this event, a critical detail we will come back to, because it is directly tied to the depth of the rupture. To understand why any of this happened at all, you have to look at the machinery running underneath the entire western edge of South America. Off the coast of Peru lies the Peru-Chile Trench, a scar in the ocean floor nearly 6,000 kilometers long, where the Nazca Plate, a slab of oceanic crust, is bathed and forced beneath the continental South American plate. This process, called subduction, happens at a rate of roughly 7 to 8 centimeters per year. That might sound trivial, slower than your fingernails grow, but multiplied across millions of years in an enormous fault surface, it becomes one of the most powerful forces reshaping the surface of our planet. This exact subduction process built the Andes Mountains, lifting them skyward over tens of millions of years as the descending Nazca Plate compressed and thickened the continental crust above it. It is also the reason Peru experiences earthquakes constantly, not occasionally. As the Nazca Plate grinds and dives beneath South America, it does not slide smoothly. It catches. It locks. Friction holds sections of the plate boundary in place while stress builds silently for years, decades, sometimes centuries, until the rock finally fails and releases that stored energy all at once as an earthquake. Not every earthquake in this region happens the same way, and the August 20th event illustrates one of 3 distinct mechanisms that produce seismic activity along this boundary. The first and most dangerous type is the megathrust earthquake, where the boundary between the 2 plates itself ruptures at relatively shallow depth, displacing the seafloor and often generating devastating tsunamis. The second type occurs within the subducting slab itself, as the descending Nazca Plate bends, stretches, and fractures deep underground, well below the plate interface. This is what produced the August 20th earthquake, at a depth of roughly 66 to 108 kilometers, inside the slab rather than on the shallow boundary between the 2 plates. The third type happens within the crust of the overriding South American plate, on crustal faults created by the immense compressional stress of the subduction process, similar to the fault systems that have historically devastated cities like Cusco. This distinction between rupture types is exactly why there was no tsunami warning after this earthquake, despite its considerable magnitude. Tsunamis are generated when an earthquake abruptly displaces a large volume of seawater, which typically requires a shallow rupture on the plate interface itself, directly beneath or near the ocean floor. An intermediate depth earthquake occurring 0 kilometers down, inside the subducting slab, does not displace the seafloor in the same way, so even a magnitude 7 event at that depth poses essentially no tsunami risk. That is a crucial piece of context, because Peru's coastline carries a long and painful memory of tsunami-generating earthquakes, and knowing the difference between an intermediate depth slab earthquake and a shallow megathrust rupture is central to understanding why this event, frightening as it was, did not carry that particular danger. Peru's earthquake history reads like a timeline of the country's national memory. In 1746, a massive earthquake struck Lima and the port city of Callao, followed by a tsunami that killed thousands and left Callao almost completely destroyed. In 1970, an earthquake of magnitude 7.9 struck off the coast near Chimbote, triggering a catastrophic landslide and avalanche of rock, ice, and debris from Mount Huascaran that buried the town of Yungay, killing tens of thousands of people in what remains one of the deadliest natural disasters in the history of the Western Hemisphere. In 2001, a magnitude 8.4 earthquake struck off the southern coast near Arequipa, generating a tsunami and causing dozens of deaths. And in 2007, a magnitude 8.0 earthquake struck central Peru, centered near the coastal city of Pisco, killing more than 500 people and leaving tens of thousands homeless, one of the most destructive earthquakes in recent Peruvian history. Each of these events shares the same fundamental cause. Each one was a release of stress that had been accumulating along the Nazca South American plate boundary, sometimes for a few decades, sometimes for well over a century. This pattern is exactly what leads scientists to something called the seismic gap theory, and it is central to why researchers are paying such close attention to what happens next in this region. A seismic gap is a segment of a fault or plate boundary that has not experienced a major earthquake in a long time, relative to its neighboring segments, even though it is subject to the same tectonic loading. The logic is straightforward. If the Nazca Plate is consistently sliding beneath South America at 7 to 8 centimeters a year across its entire length, but one particular segment of that boundary has stayed silent for far longer than its neighbors have, then stress is likely still accumulating there, unreleased, like a stretched spring that has not yet snapped. Research published in the Proceedings of the National Academy of Sciences examined this exact pattern along the entire western coast of South America, and found that over the past century alone, 6 earthquakes of magnitude 7.8 or larger have ruptured separate segments of this boundary across Ecuador, Peru, and Chile, each occurring in a zone that had gone between 74 and 261 years since its last major rupture. That is a remarkably consistent pattern, and it has allowed scientists to identify specific segments of the coastline, including one directly offshore from Lima, as having gone unusually long without releasing a major earthquake, raising the possibility that they are storing enough energy for a very large event. This is precisely why an earthquake like the one that struck Ayacucho draws such intense scientific interest, even when it does not cause major destruction on its own. Seismologists do not look at any single earthquake in isolation. They look at how it fits into the broader pattern of stress building and releasing across the entire subduction zone. Every earthquake, whether it strikes deep inside the slab or along the shallow plate interface, provides new data about how strain is currently distributed underground. Researchers use networks of GPS stations positioned across Peru to measure in real time exactly how much the ground is moving, or in locked sections, how much it is failing to move, which reveals where stress is quietly accumulating. This method, called geodetic monitoring, allows scientists to essentially watch the plates get stuck and strain silently long before any earthquake announces that strain to the rest of us, combined with historical earthquake catalogs stretching back centuries and modern seismometer networks that record every tremor. No matter how small, this gives researchers an increasingly detailed picture of where the next major rupture along this boundary is most likely to occur. None of this means scientists can predict exactly when or where the next big earthquake will strike. Despite decades of research and increasingly sophisticated instruments, earthquake prediction, in the sense of naming a specific date, location, and magnitude in advance, remains beyond the reach of modern science, and most seismologists are candid about that limitation. And what they can do is identify where the risk is elevated, based on how much time has passed since the last major rupture and how much strain the geodetic data suggests has built up. Research from Caltech examining post-seismic movement following the 2007 Pisco earthquake found something genuinely useful in this regard. Scientists discovered that roughly half of the fault movement following that quake happened aseismically, meaning the plates slipped quietly without generating additional earthquakes. Notably, one of the largest zones of this quiet slipping corresponded to an area where an undersea ridge called the Nazca Ridge intersects the heat trench. That discovery mattered because it suggested this particular area was releasing stress harmlessly rather than storing it up for a future rupture, effectively lowering the seismic hazard in that specific zone while leaving neighboring locked segments as areas of continued concern. This is the kind of nuanced, evolving picture that seismologists are constantly refining, earthquake by earthquake, dataset by dataset. The Ayacucho region itself carries additional layers of seismic complexity beyond the subduction interface offshore. Because the Nazca Plate continues to compress the entire South American continental margin as it subducts, that stress does not simply vanish once it moves past the coastline. It propagates inland, creating secondary fault systems within the crust of the overriding plate itself, in the mountains and highlands far from the coast. Researchers studying the southern Peruvian Andes have used satellite imagery and geological mapping techniques to identify what are called seismolineaments, surface expressions of buried faults capable of generating their own earthquakes independent of the main subduction interface. These crustal faults tend to be smaller and less studied than the massive megathrust systems offshore, and they are frequently left out of formal seismic hazard assessments, even though their shallow depth and proximity to populated towns can make them just as dangerous when they do rupture. This is part of why individual events like the one that struck near Coracora carry scientific value well beyond their immediate impact. Every earthquake in this region, whether centered on the main plate boundary or on a secondary crustal fault, adds another data point to a puzzle that scientists have been assembling for decades, refining their understanding of exactly which structures are active, which ones are dormant, and where future hazards are most likely to emerge. There is also a human dimension to this scientific story that deserves attention, because Peru's relationship with earthquakes did not begin with modern seismographs. Archaeological research conducted in the Cusco Basin, an area devastated by earthquakes in both 1650 and 1950, has examined surviving Inca stone, structures for evidence of ancient seismic damage, a field known as archaeoseismology. These ancient builders, working centuries before anyone understood plate tectonics, developed construction techniques using precisely interlocking stone blocks that have withstood repeated shaking far better than many modern buildings in the same region. Studying the cracks, shifts, and repairs visible in these centuries-old walls gives researchers a longer historical record of seismic activity than instrumental data alone can provide, since Peru's modern seismograph network only extends back roughly a century, while its earthquake history stretches back far longer. This deep archive of both written colonial-era accounts and physical evidence embedded in ancient architecture allows scientists to estimate recurrence intervals for major earthquakes that would otherwise be invisible to modern instruments alone. All of this monitoring work matters because Peru's exposure to seismic risk is not shrinking, it is growing, simply because more people now live in earthquake-prone areas than ever before. Lima alone has grown into a metropolis of more than 11 million people, many of them living in dense, rapidly built neighborhoods atop the very seismic gap that scientists have flagged as capable of producing an earthquake EFI, magnitude 8.5, or greater. Unlike Coracora, a rural town of 10,000 people surrounded by open hillsides, a major rupture directly offshore from a capital city of that size would test infrastructure, emergency response systems, and building codes on an entirely different scale. This is precisely why the Instituto Geofísico del Peru operates a continuous, nationwide monitoring network, feeding real-time data to the National Emergency Operations Center, so that even a moderate, non-destructive earthquake like the one on August 20th triggers immediate analysis, not just of the event itself, but of what it might reveal about the broader stress field building beneath the country. It's worth pausing on just how frequently this country experiences seismic activity, because the numbers put the August 20th earthquake into proper perspective. Peru experiences hundreds of smaller earthquakes every single month, a near constant background hum of tectonic activity that most residents never even notice. Earthquakes of magnitude 7 or larger strike somewhere in the country roughly every 3 to 5 years, while truly massive events of magnitude E8 or above occur on average once every 10 to 15 years. Living with this level of seismic activity has shaped Peruvian building practices, emergency drills, and public awareness campaigns for generations, even if enforcement and infrastructure resilience remain uneven between wealthier urban centers and poorer rural provinces like Ayacucho. The fact that a magnitude 7.2 earthquake struck a rural Andean province and resulted in no confirmed deaths is, in many ways, a genuine success story of disaster preparedness, quick evacuation behavior, and the simple luck of depth and distance working in the population's favor. It could very easily have gone differently had the same energy been released at a shallower depth, closer to a population center. Looking forward, seismologists monitoring this event are focused on several specific questions. They are tracking aftershock activity in the days and weeks following the main shock, since intermediate depth earthquakes of this size can still trigger secondary tremors, though typically smaller and less frequent than aftershock sequences following shallow crustal earthquakes. They are analyzing whether this rupture altered stress conditions on any nearby fault segments, a phenomenon known as stress transfer, where one earthquake can slightly increase or decrease the likelihood of fail, URA on a neighboring fault. And they continue feeding this new data into the broader, ongoing models of the Peru-Chile subduction zone, refining their understanding of exactly how strain is distributed along a boundary that stretches for thousands of kilometers and has produced some of the most powerful earthquakes ever recorded anywhere on Earth. None of this diminishes the real disruption experienced by families in Ayacucho, whose homes, schools, and health centers now require repair, and whose sense of safety was shaken just as much as the ground beneath them. But it does explain why an earthquake with no reported fatalities still made headlines across the scientific community, and why researchers describe events like this one as valuable, even necessary, windows into a system that is constantly building toward its next major release. There is a technical detail worth explaining more fully, because it separates informed viewers from casual headline readers, and that is the difference between magnitude and intensity. Two words that get used interchangeably in casual conversation, but mean fundamentally different things to seismologists. Magnitude describes the total energy released at the earthquake's source, calculated from the amplitude of seismic waves recorded on instruments, and it does not change no matter where you are standing when the earthquake happens. A magnitude 7.2 earthquake released the same amount of energy whether you measured it from Coracora or from Lima. Intensity, on the other hand, describes how strongly the shaking is actually experienced at a particular location, and it depends on distance from the source, depth of the rupture, the type of soil or rock beneath a given area, and the design of local buildings. This is why a single earthquake can register wildly different intensity levels across the region it affects. In this case, Coracora, sitting closest to the epicenter, experienced intensity 3 to IV, a moderate level of shaking, largely because the rupture occurred so deep underground that its energy had already spread and weakened considerably by the time it reached the surface directly above it. Meanwhile, Lima, sitting on a thick basin of soft alluvial sediment that tends to amplify seismic waves even when they originate from a great distance, still registered noticeable shaking, despite being hundreds of kilometers away. Understanding this distinction is essential to understanding why an earthquake this large did not produce widespread structural collapse, and why scientists caution the public against assuming that a high magnitude number automatically means catastrophic local damage. The technology behind how quickly this information reached the public also deserves mention, because it reflects decades of investment in seismic monitoring infrastructure across South America. Peru's Geophysical Institute operates a nationwide network of seismographs, GPS stations, and accelerometers that transmit data continuously to processing centers, allowing scientists to calculate an earthquake's location, depth, and preliminary magnitude within minutes of it occurring. This same infrastructure feeds directly into Peru's national early warning and civil defense systems, which is why authorities in Lima were able to confirm within a short window that no tsunami threat existed, and why local officials in Coracora could begin coordinating an emergency response almost immediately. Compare this to the earthquake monitoring capabilities that existed during Peru's most devastating seismic disasters of the 20th century, when information about an earthquake's true scale and location sometimes took hours or even days to reach the outside world, and the improvement becomes clear. That said, monitoring technology can tell scientists what is happening, and to a limited extent, help estimate what has already happened deep underground, but it still cannot forecast the future with precision. Instruments can detect strain accumulating along a locked fault, and they can flag a region as carrying elevated risk. But converting that risk assessment into an actual prediction of the next major earthquake remains one of the most difficult unsolved problems in all of geophysics. This is also why international collaboration plays such a significant role in studying Peru's subduction zone. Researchers from institutions including Caltech, the Institut de Recherche pour le Développement in France, and numerous Peruvian universities have worked together for years, installing GPS networks, analyzing satellite radar data, and comparing notes across national borders, because the Nazca South American boundary does not respect political lines. The same subduction system responsible for Peru's earthquakes also generates MEJE, or seismic activity in Chile, including the 1960 magnitude 9.5 earthquake near Valdivia, still the most powerful earthquake ever recorded by modern instruments anywhere on the planet. Studying how stress redistributes across such an enormous plateau boundary requires exactly this kind of cross-border, multi-institutional effort, and every earthquake, including relatively moderate ones like the August 20th event, contributes another data point that researchers on multiple continents will study for years. For residents living across these seismically active regions, scientists and disaster preparedness officials consistently emphasize a few practical points that remain true, regardless of exactly when or where the next major earthquake strikes. Buildings constructed with reinforced materials and modern engineering stand. Hards perform dramatically better during strong shaking than older adobe or unreinforced masonry structures, which is why post-earthquake damage in Peru so often concentrates in poorer rural communities rather than newer urban construction. Having a clear evacuation plan and knowing safe open spa, seas away from unstable slopes and building facades can make the difference between a frightening experience and a fatal one, particularly in mountainous areas prone to landslides during shaking. And perhaps most importantly, understanding that aftershocks can continue for days or weeks following a significant earthquake helps communities remain appropriately cautious rather than assuming the danger has fully passed the moment the initial shaking stops. These lessons, learned and relearned across decades of Peruvian seismic history, are precisely why the response to this latest earthquake, despite its considerable magnitude, unfolded without the loss of life that so many previous events in this country's history have brought. Peru sits at one of the most active junctions of the Pacific Ring of Fire, a horseshoe-shaped zone circling the Pacific Ocean where roughly 90% of the world's earthquakes occur, driven by the collision and subduction of massive tectonic plates from Japan and Indonesia to Chile and Alaska. What happened in Ayacucho on August 20th was one relatively small sea happened within that immense planet-spanning system. But it was a chapter that scientists read closely because every rupture along the Nazca South American boundary helps refine our understanding of where the next major earthquake, the one capable of striking a major city rather than a rural highland town, is most likely to occur. The mountains, the earthquakes, and the very shape of Peru's coastline all trace back to the same relentless process happening beneath our feet. A slow-motion collision that has been building the Andes for tens of millions of years and will keep generating earthquakes for as long as the Nazca Plate continues its descent into the earth. Thursday's earthquake was a reminder, not of destruction, but of the enormous, patient forces constantly at work beneath a country that has learned, out of necessity, to live alongside them. If you found this breakdown valuable, hit that subscribe button and turn on notifications, because we cover major earthquakes, natural disasters, and the science behind them as they happen around the world. Drop a comment below and let us know which region you'd like us to cover next. And if this video helped you understand what's really happening beneath Peru, give it a like and share it with someone who needs to see it too.